Greetings, Cal 3. Today we're going to talk about vectors. Vectors are something very, very important to talk about before we jump off into parameterizations. Vectors are something with distance and direction. In this class, we use the parenthesis notation for vectors, right? Where we put our x coordinate right here, our y coordinate right here, our z coordinate right here, right? And this is something with distance and direction. A point in space, while it may use the same notation, means something much, much different, right? A point in space has no distance and it has no direction. It's simply a point fixed in space. By distance, we mean something like a norm, a length, a magnitude, depending on when we're talking about this and where we're talking about this, heck, even what book we're talking about, right? They can be referred to in many different ways. A norm is the most mathematical way to talk about this. And in this class, we use what's called the Euclidean norm, which we'll talk about in just a second. And we use direction, right? Direction are our coordinates in our space. Now, it doesn't necessarily need to be Euclidean space for a vector to work out, right? There exist many, many types of vectors, and we'll explore some of them throughout the course of this semester. So, let's first build our intuition of like how we form a vector. If we're talking about R2, so we say let V come from R2. It's a vector. We can put a vector symbol on top of the vector, right? If we're into that. But for the course of this conversation, right? If it has a vector symbol, it is a vector. If it doesn't, it is not a vector. It's a point. And we'll say and let P0 be 1, 2, P1 be 2, maybe 3, right? Let's make it a 4, just for good measure, right? So we call this P0, P1. Both of these live inside of our two-dimensional space, right? But they're points, right? No vector hat, and sometimes we'll see a bold face, right? These are just points living inside of space. If we were to plot these points, these mean I go out 1 in the x direction and up 2 in the y direction. Here, it means I go out 2 in the x direction and up 4 in the y direction, maybe or something like here. Now, if I wanted to have the vector v, right, that goes from point 0 to point 1, so we'll call it v is p0 to point 1, p0, p1, right, starting at p0 going out to p1. We start at p0 and we draw our vector out to p1. So here's p0, here's p1, here's our vector v. Vector v necessarily is how much should we change in the x-axis and how much should we change in the y-axis. Okay? And how do we do that? Well, we have our point in space, we have our other point in space, and we have our vector, right? We're going to go out some x directions, up some y direction. Well, how can we figure out how far we went? Well, we know we have some x coordinates, right? 1 and 2. So we know here we're at 2, here we're at 1. So that means that we've gone out 1 in the x direction, right? We know that our vectors are necessarily orthogonal to each other, that are going to build up our vector. We call these I and j, right? So we're going to go up 2, right? In the y direction, 4 minus 2 is 2. So this means that our vector v has the coordinates in space 1, 2, right? So we've gone out 1 in the x direction, up 2 in the y direction. And this can also be referred to as I hat plus 2 j hat. Where's a 1 in front of that? I hat, right? Which simply means we have 1 I hat vector in our direction and 2 j hat vectors. Where I hat and j hat, again, right, are those unit vectors in the x and the y direction, okay? If we wanted to figure out the length slash the magnitude slash the norm of our vector v, denoted by 2 bars about it, it's going to be the square root of the sum of the components vi squared, right? And where each vi, so v1 in our case would be 1, right? Because v was equal to the vector. That's not a vector, right there. 1, 2. So v1 be equal to 1, v2 be equal to 2 in our case, right? So the magnitude of v is nothing more than the square root of 1 squared plus 2 squared. That's nothing more than 1 plus 4, which gives us root 5. So this vector has length 5. It has a direction in the direction 1, 2, and has a length of 5. All right? Now that we have that in the bag, let's talk about how we might want to add these vectors to each other, right? So let's say we have two vectors. I have vector 1, that's going to be 1, 2. And I'll have vector 2, that's going to be 3, 4. Now these are vectors, right? We could say vector 1 plus vector 2, that's going to be 1, 2 plus 3, 4. We're going to add our x direction, add our y direction. Why is that? Well, if we think about the tip-to-tail addition of our vectors, here's, say, v1, here is, say, maybe v2, right? v1 is added to v2. We do what's called tip-to-tail. The tail of the vector, right, the piece that doesn't have the arrow, goes on the tip of our old vector, right? And we're going to go out some x direction, and we're going to go up some y direction, just as we've always done, right? We're going to make our new vector v1 plus v2, right? Now what this is going to tell us is we're going to get all the x direction from v1 and all the x direction from v2, right? So v1 had 1 in the x direction, v2 had 3 in the x direction. v1 had 2 in the x direction, v2 had 4 in the y direction, right? So this means that in all, we're going to have 1 plus 3, that's 4 in the x direction, 2 plus 4, that's 6 in the y direction. And that's how we add vectors, which is going to be very, very important right when we start dealing with parameterizations. So, in the spirit of dealing with parameterizations, which is going to be coming in the next video, suppose I have my vector v, right? And I want to have 2v, right? I claim is going to be the length of v, right, doubled. Maybe that's 2v, right? And if we think about this, 2v is simply v plus v, right? Addition works. So it's going to be our x-coordinate, right? And our x-coordinate again, our y-coordinate, and our y-coordinate again. We get 2v, double the length of v. If we say v is something like 3, 4, the vector, then 2v is nothing more than 6, 8, which is 2 times 3 is 6, 2 times 4 is 8. And finally, if we had our vector, we'll call it v, and we'll call this vector right here w. If we wanted to add v to w, right? Vectors are not necessarily located in space. They simply have a direction, right? So we can move them wherever we want. Let's move w on up to v, and we get w. Okay? Now suppose we wanted to do, and then this vector right here, right? This would be v plus w. Now what if we want to do something like v plus 2w? Well, we know that 2w will be w, and then on itself one more time. So we get 2w, bringing this vector up to v. Maybe it goes out to here, right? And this is going to be 2w, right? Twice the length of w. The vector v plus 2w is going to go out to here, right? And it's going to have coordinates. If we have v to be coordinates v1, comma v2, w to be coordinates w1, comma w2, then v1 plus 2, v plus 2w, if we're going to keep consistent with our notation. Right? This will be the vector v1 plus 2w1, comma v2 plus 2w2. If we were to plug in numbers, we would get back out the proper vector. That would be the addition of a vector and some scalar multiplication. If you want some more information on vector space, I think I'm going to link a Wikipedia article down below that talks about what exactly is a vector space and all the cool properties that can come out of it. I hope you enjoyed this video. Tune in next time when we talk about the parameterization of a line segment. See you then.